All right, physics fam, we are back. Steps of the scientific method is what we'll be covering today. This is obviously a recap and review, so hopefully we can fly through this, but important things we always have to consider. We know the scientific method is basically a series of steps we're going to use to figure things out. Let's look at those steps. We'll go through each step, but we fully know from other classes, chemistry, etc., you start with a problem or question, you observe and look into it, you eventually think of what are the effects that are occurring here, so what's happening. We want to get some type of experiment in order to figure out the answer to see if our hypothesis is true or not. We get our results, put it all together, and hopefully get a conclusion, though in reality we're fully aware the conclusion isn't always easy as just one experiment. Sometimes we have to go back and try other things, so keep that in mind. First things first, natural curiosity is number one for science, right? So we have to have a problem or a question to end up answering and figuring out. We then want to be educated on the topic so that we have a better idea of the entire situation for a specific problem. From that, we can end up forming what we know as a hypothesis. We often call that an educated guess or something like that. But a lot of times hypotheses are written well if we do the if-then kind of statement. So for example, if soil temperatures rise or go up, then plant growth will increase as well. So that if-then relationship is often a good way to start when we write a hypothesis. Now, a hypothesis is only good if we can actually have some type of controlled experiment to help prove or disprove it. So, we set up an experiment by getting a procedure, a list of materials, and end up trying to find a way to get some measurable data. Another way to say that is quantifiable data. But we want data that can help prove or give evidence to either support or go against our hypothesis. Remember, without a controlled experiment and too many variables going on, we have no idea what affects what, and we end up not getting a really good, decent answer. So throughout our experiment, we have to collect and we have to analyze those results in order to get data to figure out, hey, is my hypothesis right or wrong? A lot of time when we have that data, it's good to put it in tables or graphs or have pictures of it. Not only to have evidence of that, but sometimes a table, a picture, or a graph can organize our data in a way where we can see trends. And oh yes, there is a relationship between these two. For example, as the soil went up, yes, most of the plants grew larger and larger. Okay, that would be support in the earlier hypothesis that if soil temps get hotter, then plants grow better. Once you have all your data and you organize it, we finally can get to the conclusion part. Getting the feeling of, hey, is my hypothesis correct? Do I accept it or do I reject it? Sometimes you can't do that. The experiment didn't go as well as planned. You ended up having more variables than you anticipated, and you actually have to go backwards and start over and make the experiment even better. That is true science. It's messy. It's sloppy. What experiment you started with that you thought would give you some good conclusive data ends up being something that is kind of a mess, and you have to say, okay, I need to fix this, this, and this in the experiment, and then redo it with new data before I can draw my conclusion. So remember, in classroom, our labs tend to go pretty straightforward because we've already thought ahead of what's a really good experiment to prove our point. But when you're starting from scratch, that's going to be a messy thing. It's going to be a lot of tweaking and redoing, etc., in the experimental phase before you can get to the conclusion part. Once you get your results, you can communicate those ideas, whether it's in a lab write-up in class, whether it's in a scientific journal, etc. But those are the steps people take. So let's do a little bit of an example and walk through the method of something that's a pretty simple experiment that maybe someone could do. This kid watches his grandma bake bread and notice that the yeast gives off gas that feeds on sugar. So if you've ever made bread, you know this. You need sugar with the yeast to feed it in order to get carbon dioxide, in order for the bread to rise. So this kid naturally thinks, hey, if I put more sugar, would the dough rise even more? That's a natural question, or what we can call a problem. Now, it's not a life-changing problem where, if he doesn't figure it out, his life won't be fulfilled. But it's a good natural question. Hey, if there's more sugar, will the bread rise even more? So now the boy's looking for the effect on the actual bread from the sugar. But remember, effect and affect are two different words. And we use those a lot in science, and I don't want you to use them wrong. Effect is technically a noun. So what is the effect of the sugar? The effect means that it's a noun, so it's with an E. But affect is a verb. So how does the sugar affect the rising of the bread? Would be like a doing thing. So effect is a noun, affect is a verb. Remember that. That'll be helpful when we're writing out different lab reports. So this boy John looks into, hey, how do we actually make bread and let it rise, and how does that work? So now he has an understanding and knowledge of making bread, which can help lead him to eventually getting to a better experiment. He ends up talking to his teacher and kind of diagramming out an experiment, and the teacher gives him some hints and ideas of, hey, is this controlled, is this not controlled? After all his research in that, he finally says that his hypothesis is, if there's more sugar, then the bread will rise higher. Notice it's that if-then statement. Important to remember, though, if it's a true hypothesis, we have to be able to test it. So let's see if this kid comes up with an idea that you can test. Remember that hypothesis is that educated guess. It's an informed guess of what you think should happen. Do you know for sure? No, that's what the experiment is going to do. When you do an experiment, there's a relationship between the independent and dependent variables. Remember, the independent variable is the thing that you're going to control. I imagine in this case, John is going to control the amount of sugar. The dependent variable is what's affected because of what you changed in the independent variable. So in this case, the dependent variable would be how high the actual bread dough rises. So again, to recap, independent variable is what we control. In this case, it's going to be the sugar. He's going to put different amounts of sugar in different loaves of bread. As you know then from previous classes, the dependent variable is what actually changes as a result of changing the independent variable. All right, so in this case, it would be how big that loaf of bread is. Teacher once again helps John work out, hey, what steps should you take, and make sure that we have a control group, something to compare everything to. Recap, if you don't remember what a control group is, it is that standard of comparison. It's what everything else is compared to. So it would be no treatment, or in this case for John, it would be something he selected to compare all the other loaves of bread to. I imagine he'll pick his grandma's original recipe. It's important to remember that all experiments should have some type of control or control group. You have to compare it to something. And as I stated earlier, since his grandma normally used 50 grams of sugar in a recipe, that's what's going to be his starting control group. So he's going to have sugar with less and more than his grandma's recipe, and he'll continue to compare it to his grandma's original recipe. That's a control group. The teacher reminds him, you got to keep things constant, so control. Everything has to be the same. The only difference is the amount of sugar in the recipe. Every other thing you should try to keep the same for every loaf of bread. And that's what John tries to do. He has to figure out what can he keep the same for everything. So he makes a list. The recipe stays the same. The type of oven used, the amount of rising time, the brand of ingredients, the cooking time, the type of pans, the air temperature, how much humidity is in the air, where the bread's rising, oven temperature, everything. All those things stay the same. The only difference is, of course, the sugar. The sugar amount will be variable. Otherwise, everything else should be constant. That's a good setup for an experiment. All right, so he writes out his procedure, and basically it's like a recipe, step by step, of what he's going to do. That way he is less likely to make a mistake in his experiment. John decides he needs different trials. So besides having the different amount of sugar, he's going to try each amount of sugar or loaf of bread 3 times. That makes sure that there's not some freak accident that happens, but with 3 tests of each type of amount of sugar, that should give him a better idea of what's going on, and if there's a true relationship between sugar and rising in bread. John figures out ahead of time, hey, I've got a table I can use to write down all my information, the amount of sugar, how high the bread rises, etc. That's a good way to organize your information so that you can collect and analyze your results. Remember, there are two types of data. We can take quantitative data that uses numbers that are measured. That's what we really like in science, quantitative data. So qualitative data can be helpful, but that's telling you about the qualities or characteristics of an object. For example, the bread might feel soft. That's not a number associated with the data, so it's not quantitative, but it still could help you out in making different observations. But we love quantitative data in science. So John's a rock star, gets all of his information, figures out with 25 grams of sugar, this is about how high in cubic centimeters the bread loaf is, how much volume I should say, compares it to the control group, compares it to 100 grams of sugar, and compares it to 250 grams of sugar. When you look at a chart, you want to definitely see if there's any trends involved. So you can see that there's an increase in size as you go up, and then all of a sudden, there's a decrease in size. So there must be a sweet spot for the bread with how much sugar you give it before it starts to actually hurt the bread. So it looks like the control group, Grandma's actual original recipe, gave the bread the highest amount of rise. That makes sense. If that's an old recipe from the family, they probably figured out over the years what the best amount of sugar is to get the most bread. But regardless, this is important information to help John come to a conclusion about his hypothesis. Now, what we just talked about in that last slide is what he's doing now. He's looking over it to see that, hey, when I get to 100 grams of sugar, it's really not that much better than the 50 grams of sugar. So that must be a really good recipe. He ends up saying that that's not true. The more sugar you add doesn't necessarily mean the larger the bread is. In fact, between 50 and 100 grams, it doesn't seem to help anymore. If anything, it hurts it. So that's a good conclusion he drew from that. He can retest it and focus on between 50 grams and 100 grams to see if there's a sweet spot where maybe he could get that bread a little bit bigger. Maybe it's somewhere in between here, like 75 grams. Who knows? But he can test that out with a very similar experiment. You got to ask yourself, are there different groups that did better than others and why? So we want to continue to analyze our data. When he ends up doing 50 to 80 grams of sugar, he notices that it increases, and then decreases at 80. So it looks like the sweet spot here is 70 grams of sugar. You get, on average, a larger size of bread compared to the other ones. So not only did he figure out Grandma's recipe is good, but he could technically improve it a little bit with an extra 20 grams of sugar in Grandma's recipe to make it bigger, if you want bigger bread. So Johnny saves the day. He could go and tell Grandma, hey, Grandma, you want your bread even bigger? Throw 70 grams of sugar in there next time. I've got the data to back it up, and his second hypothesis was accepted. Pretty impressive. Nice job, John. He not only tells his grandma, but he tells his science class, which is good, communicating the results. The world can't excel in science if people don't know about it. Obviously, this is just a loaf of bread, but for other experiments and research, we need to let the world know what we find. Hopefully you saw the steps taken in a scientific method. Notice that he had to retest, retry, redraw up his hypothesis. Learning's messy. Science is messy. It doesn't always work perfectly the first time around. You have to make improvements. So keep that in mind. When we do things in the lab, sometimes you're going to have to do them over again because you didn't make it controlled, even though you could have. So keep that in mind. But hopefully this is a great recap for scientific method. Take care, physics fan.